what I want to do next is to say something about the possibility for what we could call wide area control. And then I come more back to wide area protection tomorrow in one application. Then the question is there a need for that? So you have to ask yourself, when is it relevant or when is it necessary? When is it good to utilize PMUs for power system control? I would say that that is not obvious that it is, but you could say when there is a need for system-wide information, if you cannot measure what you need for the control locally, then there is a reason to do wide area control, of course, or use PMUs. But it also should be a requirement for high resolution dynamic information, or less, or otherwise you could use SCADA measurements, for example. So you have to, there must be a need for the high resolution data. Or if you need time synchronized measurement, of course, then you have a reason to look into PMUs for control as well. So what kind of applications could that be? It could be related to power oscillation damping, for example, because we know that is a system-wide phenomena, can be. It might be something like monitoring or doing the right actions when you get a frequency instability or a risk of islanding of the system. It could be related to some emergency controls that I touched upon briefly with the system protection schemes, that you need to have a system-wide look at this before you take decisions. It could be for protection against a voltage collapse, where you could have more reliable detection if you have wide measurements from more than one place in the system. That is some examples that I can come up with. Maybe you have others. And then how would we do it then? We could look into power system stabilizers, how we could utilize PMUs for coordinated design. We could look into control of static VAR compensators or other fax devices, how you could optimize the use of that, including also high voltage DC converters. Now with more and more of the high voltage DC links being voltage source converters, you could utilize them for many purposes other than transmitting power. You could use it for sort of controlled islanding. And you could use it for what is more advanced or improved system protection scheme, like generator tripping or load shedding. The project that I have been involved in regarding wide area control was with the objective to design what we called a wide area power oscillation damper, and that is essentially a traditional power system stabilizers applied on a static VAR compensator, but with measurements from not just local, but from PMUs in the wide area. The objective for that would be that we want to target possibly more than one mode As you have seen, in some places you have um, 2 or more modes involved in the dynamics, so it's not easy to discriminate what is the problem, what is the mode, critical mode at hand, or how to design your controller. Then you could utilize wide area measurements in order to get better observability of the critical mode. So you sort of, instead of filtering your local signal, you select signals which has a good information about the mode in question. You could also do something about the controllability by sort of using several PMUs, make sort of a multivariable controller. Okay, you see, I thought I had a map there, but it comes later on probably. So essentially what we wanted to make is a robust design, ability to improve damping in the largest possible range of operating conditions, possibly involving more than one mode. And we want to do a coordinated design to avoid adverse interactions. Again, the starting point is the analysis I showed earlier on. Here with another picture showing exactly what we tried to say before. We have this 0.5 Hertz mode that is characterized by a generator oscillating against each other here. And the other 0.3 Hertz mode that's characterized by these oscillations. And both are sort of seen, observed here at the corridor that we are looking at. Again, the same case. SVCs, we have, as I indicated, quite a few of them in the Norwegian system, from the far north down to the south peak. In this case, we are utilizing the SVC that is centrally located here, close to what we would call this the critical corridor. We started out with analysis, both small signal analysis and transient analysis, and we observed that with our controller we were able to damp both these critical modes. 0.3 Hertz mode initially here was shifted very easily to the left. 0.3 Hertz mode also. This was with the wide area measurements. This was with the local measurements. And the difference that we see is not dramatic, but it is significant in a way, it is still in a way, because, well, we see that the 0.5 Hertz mode is not really a problem. It's fairly well easily shifted. 0.3 Hertz mode takes a little bit more effort, and it's slightly better with the wide area measurements because we're able to measure that better. But the other thing is that there are other modes that can be adversely affected, which is it does up here, for example, and here. But these modes are also actually improved with the use of wide area measurement. So that's sort of, we thought that was promising results, so we wanted to go ahead with that. Main conclusion, we thought we could conclude that wide area solution could be more robust than local measurements, mostly because PMU measurement enhances the observability of the modes at question. And then, of course, there were some questions that we had. Would this work in reality? What about the availability of communication? What about the latency? the delays due to communication. What would we do if the communication were lost? Would we have a blackout because we lose communication to the PMUs? These are the serious questions. And that needed experimental testing to address. So some years ago we did a field test on that at the substation. We tested the wide area power oscillation damper that we had designed on a 180 megawatt thyristor controlled reactor. So it's it's an SVC unit, but only with thyristor controlled reactors combined with capacitor bank, so it worked as a SVC. So we excited the system by disconnecting and reconnecting lines in close to the site, and we tested and compared the performance against the conventional or state-of-the-art power oscillation damper that ABB manufactured, and without any POD. So now I think this picture is best. Again, our measurements, ideally we would have wanted measurements from Finland, because that would have given us better observability of the 0.3 Hertz mode. But electrically, this site here in northern Norway is closer to Finland than other places, so we selected that. The other measurement point was down in the south in Norway. So what we did, we measured the voltage angle between this station and this station. And that was then fed to the static work compensator and the POD that was placed here at the Hasle transformer station. This was all implemented in ABB's state-of-the-art controller at that time, with the local control, with the wide area POD, and with a switch over logic that I will explain. If you wonder how a thyristor control reactor looks like, this is the picture of the reactors. And of course the thyristors that controls the reactors are inside the house here, and it doesn't really, it's not that impressive. The reactors are old, but the control system is new. So the reactors, they are here, correspond to reactors here and here, with the thyristors to switch them. And this is placed, if you look at the map, there are two lines coming in here from the west and two lines going further towards Sweden. These are the two lines coming in, and these are the two lines coming out. And the controller, the traditional controller of the TCR or the SVC is a voltage controller, perfectly analog to the AVR on a generator, measure voltage, have voltage set points, and controls the effective susceptance of the reactor. And it is equipped with auxiliary control input that is usually the local POD, which measure the power on the line. But what we developed then was the wide area power oscillation damper that took the angle difference from the two remote sites through the controller and added that as the control signal. And then we needed some switchover logic here that worked in the sense that if the latency of the signal in here was discovered to be too long, or the communication was lost, then we would switch over to the local. So it was sort of no risk involved in that, and it's a solution that works. Then this is the backup, yeah. Yeah. It's for safety, sort of. Or it usually, I mean, you need to protect this against giving wrong signal. If it's no signal, then it's usually okay, but the wrong signal could be dangerous. Yeah, that's the main thing. So we tested this. The result is not that interesting or impressive, because the system was fairly well damped in this week that we did the tests. We switched the line, switched out one of these lines coming in, made the system, excited the system quite well. So we see that in the voltage angle difference that changed with a number of degrees. And well, clearly the worst performance was without any, or not, it's not obvious actually here which was worst. If it was the no pod case or the local pod case when you look at the angles. But I think we were able to conclude that the wide area pod was slightly better, even though no big differences, because due to the good damping. Well, I can show you more figures on that tomorrow, but the main conclusions anyway was that it performed as intended, and also fully according to our expectations based on the simulation results. And of course, these in reality, it depends very much on how good your local measurements are. Depends on the actual tuning of the compensators and so on. But I think we could say that the flexibility provided by the wide area pod to select best measurements from available PMUs as control input is an advantage that could be exploited more when you have phasor measurement in more and more places. And it was good to see that the end-to-end latency due to the communication from the remote measurements was mainly insignificant, in the order of 30 milliseconds, which is then more than sort of 10 times lower than the Nyquist limit for this application. Okay, then I would like to spend the last minutes on saying something about the Nordic collaboration that Professor Kjetil mentioned briefly, which we are following up now. And I will talk, this is sort of also an introduction to the further work that I will talk about tomorrow. This is the Strong Grid project that we had with participants from actually all the 5 Nordic countries. These are the flags of the 5 Nordic countries, including Iceland, but also the Baltic countries that are Latvia and Estonia. And the transmission system operators in Norway, that's Statnett, Swedish Power Grid in Sweden, Fingrid in Finland, and Landsnet in Iceland. The Danish TSO Energinet was not part of this project. The goal was just to try to create applications that enable better operation and control of the power grid, with emphasis on PMU and VAMs as the enabler. What we wanted to do was to develop a research platform and software interfaces in order to develop these applications. So the way of doing this, which is not very advanced, but it sort of worked for collaboration, is that we all had some PMUs in our laboratories. We had the National Instruments LabVIEW implication. Others had ABB, had borrowed or bought PMU from ABB, other from SEL. And we hooked this up to our own PDCs, those of you that had PDCs. And we could stream the data to each other. So these were available, online PDCs and installed PMUs, online PMUs at our site, at KTH in Stockholm, at DTU in Denmark, and at Aalto in Finland. Also later on, the Baltic countries had PMUs, but a thing to say about that is that even though the Baltic countries are connected by HVDC, they are on the AC connected to Russia, so they are on the Russian frequency, we might say. But it's interesting still. So a more detailed picture of that with our equipment. I won't go into detail here, but the idea was that everybody streamed out data to all the other participants. This is just a picture of the lab at KTH in Stockholm with some of their equipment. This is a picture of a software kit that enabled us to make application without too much effort. So it's a piece of software within a LabVIEW environment that made it simple for us to access the PDC or the PMUs by just entering the IP address and some port numbers, and then we could add on with applications. So that's a real benefit to have this kind of software. So you don't need to understand all the details about the communication aspects and how you stream data. Here is I don't know if this is the latest, but there was a question about protocols and standards. I think this is the one you should look for. Maybe there are updates now. IEEE C37118. So from the project, we looked into various, let's say, problem areas: angle stability, voltage stability, state estimation, protection, ICT, a little bit on ICT, one PhD. And there were two various sort of, let's say, we often talk about TRL levels, technology readiness levels. You could say that these applications that were developed is at various readiness levels, but many of them are at the level where they can be implemented as, or are implemented as, prototypes. So that is some of the applications that I want to talk about then tomorrow. So that's very briefly that, and to concluding remarks about that is that I think it was important to have this collaboration to sort of improve our competencies by mutually learning from each other. It resulted in, I think, at least 5 PhDs up to now from this, and courses and other prototypes. And also the fact that the TSOs, transmission system operators, has really started to work harder, been more interested in this topic. They're starting deployment and pilot installations. And also the TSOs are motivated now to continue the R&D collaboration in this area. So that is some of that follow-up projects and applications is what I want to talk about then tomorrow. Just look through, see if there are, we are starting to come into applications that I will talk more about tomorrow. But what I will not talk about is this one, because I don't know it, but I can, for those who are interested in that kind of topics, for example, estimation of line parameters and by PMU measurement is something that was done. Because of course line sag is a critical factor, especially in forested areas like in the Baltic countries, where it's essentially the whole country is forests. That is also in Finland, but you want to know if this will sag into trees or down to the ground. PMU lab. Just scroll through it, see if there is something I haven't touched upon before. So this is the general conclusion. The future is electric. So I think, is this a good time to stop now and continue tomorrow before the audience fall asleep? Yeah, we have time for questions. Yeah.
technique to damp out the oscillation. This is one of the results. And then if you can, maybe I can.
Please go ahead.
Because you touch it a little bit tired.
Yeah.
Because if you look at the last slide actually, which you have shown to me. Because what if you look at this one, this part,
Maybe I turn it off. A sec. Yeah, the middle one.
Because,
No, this is better.
in the stronger project, actually, they have developed an app actually. So this is an app on the tablet, and another you have it on the phone. So, so thus you have an app available on the tablet or the phone, and then they have the complete visualization toolbox. So thus the operator can know, okay, what is the variation of the frequency in the system, in the Nordic gate system, I mean. So because they have the low voltage PMOs installed in their lab. So that is one way, this is one the kind of result which you have developed out of the project. And then again, the other one, if you look at these results, if you have some oscillations, this is actually force oscillations. So they have a toolbox, visualization toolbox to detect the force oscillations, and then again to assess the voltage stability. Then again, there is another visualization toolbox for inter-area oscillator, and this part actually, this is a color map which we refer it as. So from here we can know what is the most sensitive frequency of oscillators. From that part we can know. And then on this part, because we have the several PMOs installed in the Norway grid, so it is possible that with the use of the PMO signals from this point, the phase of oscillation can be monitored. So that is how they have worked on in the development of visualization toolbox out of the project. In fact,
I can check if there are some some online now.
based on the PMO application, I would say.
Where do I have that, you see? I almost forgot where I have it, but could it be here? I will ask my colleague tomorrow to check if this is update, but it's it could give you some idea. I mean, when I select the PMUs, I need to select in this case, select the IP address of the PDC that I'm connecting to, and some port and some code, and then if this is correct, it should work right. But if it does now, I don't know. But I will ask my colleague to start the PDC tomorrow so that we can demonstrate it.
This laptop, because last time you had a different laptop from StatNet.
Yeah, but this is with this I can only access the PMUs from our lab and from KTH and from the universities if they are available. Lately there has, at least one from Alto has been available. And I will ask if we can have other hours. It seems that it's not up and running, the PDC. But tomorrow maybe we can ask him to start and show you at least. Show you the information we get from there.
Because he has the laptop, and then with the laptop available, and then having the connection to the server with the PMO in his university, he can show what is the actual real-time signal variation or the angular signal or maybe the frequency. So that means being over here using his laptop, and then with the toolbox that he has developed, he can connect to the server in the NTNU or maybe some other, because they have it in the Alto and even the KTS. So from there, he can know what is the actual real angle variation of the signal at that location. Because last time when he was here in the conference, so he has demonstrated how we are able to monitor the angle variation of a signal being at a 190 for a system which is located quite far away from here. So he could do that.
Hmm?
Projectors.
Or, but that's okay, because then we can end the day. You can just shut it down. Depends on what you want to know. I mean, there's need to estimate for to voltage angle at the node. But you can have a state estimator to estimate other voltages where you don't have a measurement, right? Yeah. And if you have full observability, you could also estimate other parameters like the impedance, for example. So it's up to your fantasy to sort of, or models, or to think of things you can estimate or identify with the measurements.
So this means we can conclude that PMU does not completely replace the state estimation. Still
Try without the mic. Your voice was better without. I can read that.
Completely replacing the state estimation?
No, not completely, but that if you talk about the classical state estimator, of course it could replace that if you have PMUs at all nodes, or not all, but at 50% of the transformer station. You could do the same as the classical state estimator. But in addition, and that's the point, you have the possibility to estimate much more. Because you already have measured the variables that you estimate with the classical state estimator. And then you can use that to improve other things. That's how I look at it, at least. Maybe you have, yeah.
Because with the PMU, it's the information about the angle, the voltage angle. And then from the voltage angles or the current angles, you can estimate other state values. That is because what I understand, frequency you cannot just get it directly from the PMU. But from the angles, you are able to know what is the frequency information.
State estimation, not the same architecture. Calculate the voltage magnitude of triangle on the bus.
Yeah, because with all the states can be measured, I think, from the PMO. This is the problem, I think. Because once we have the angle, because that's the actually beauty of the PMOs. Because if you have the angle, voltage angle or the current angles, from there any state can be obtained actually. Any state can be obtained.
But then there is the other dimension to it. When we talk about state estimator from a power system point of view, we talk about static, the estimation of the static system, the power flow in a way. But of course, if you talk to a guy from control engineering, he thinks about dynamic. That is something to be or could be developed, right? Or look dynamic state estimator to estimate some of the state variables that we have in our dynamic model, which we don't do today. We like the internal, show the generator and those that we use.
In terms of static estimates, the PMU is more useful for dynamic one.
Yep.
Dynamic
Well,
states.
that's why that's why I say
Because,
that
you have a signal, PMU signals available at 50 hertz or
Mhm.
60 hertz, or maybe even the low rate PMU signals when it over 25 hertz. So in that case, dynamically varying signals are measurable, and then it is better to have a dynamic state estimation rather than static state estimation actually. So otherwise, SCADA, what you have, that is more than sufficient if you want a static one, static state variable, if you want that. So we are interested in the dynamic variable, dynamic quantity variables. We are interested in know more because if you look at the some of the blackouts or the oscillations which we normally have, although if you have the low frequency oscillations, though they have a very 0.3 hertz, 0.4 hertz, 0.5 hertz, right? It's a low frequency oscillation. But if you look at the blackout occurrence because of the low frequency oscillations, it has occurred just in few seconds. So in that sense, the dynamic state variable, if you want to monitor, that will be more useful rather than going for static state variable. You can say, because we are interested to secure the system stable. We are interested that way. Anything more? No. Okay.
then we'll start again tomorrow, right?
Tomorrow?